This lecture is on kinetics, chemical kinetics to be more specific. So kinetics, you've heard of kinetics before. You generally associate that with motion. Maybe you know that kinetic energy is 1/2 times the mass times the velocity squared. Well, in this chapter, we're going to talk about chemical kinetics, and we're going to be looking at changes in concentration over time. So, section 1 is on reaction rates. There's ways to determine reaction rate or changes in concentration over time. Section 2 is on dependence of reaction rate on reactant concentration, dependence of reactant concentration on time, and dependence of reaction rate on temperature. The last two sections are on reaction mechanisms. So we'll find out that most reactions do not happen in one step, that there are multiple steps required for a chemical reaction to happen, and that the slowest step is the rate determining step. And then the last section is on catalysis. We're going to look at both homogeneous and heterogeneous catalysts, and these catalysts lower the activation energy, which speeds up the reaction. So this section, we have average rate of reaction, we have instantaneous rate of reaction, and then we have stoichiometry and reaction rate. So this section is all about reaction rates. And the difference between average rate and instantaneous rate, you already probably know this. It's like if I'm driving from Lexington, Kentucky to Louisville. So I have a rate. It's a speed is distance over time, and I could start a stopwatch in Lexington, stop it in Louisville, and then take the mileage that I covered divided by the time, and I would get the average rate. And then if I want to know at a particular time between Lexington and Louisville what my speed was, that would be an instantaneous rate at a particular moment in time. So we're going to talk about in this section how to calculate average rates of reaction, how to calculate instantaneous rates of reaction in regards to a chemical reaction. So I like this slide. This is a nice visual of what a chemical reaction looks like. So first of all, we have reactants on the left-hand side of the chemical yield sign. And in this case, the reactant is reactant A. And then we have the product on the right-hand side, and that is product B. So reactants, this is what we learned in Chem 170. Reactants on the right, the chemical yield sign, and then the products on, the reactants on the left, the chemical yield sign, and the products on the right. And so in this case, we're just going to have reactant A being converted to product B. So when we look at the slides down here, at time 0, all we have is A, indicated by these gray or white dots. And as time progresses, we see that A is converting to B, and so we see the red dots forming, which is B, and we see that B increases over time. And then what we notice is that, as you know, we see huge changes in B here, and maybe a little bit and some change here. But once we get out into this region, notice there's not much change between A and B. So how would you plot that? How would you, if I had a plot here of the concentration of B on this side and time on this side, tell me what that plot would look like. So you may want to stop here and draw a picture of this. All right. So B starts out at 0. It rapidly increases, and then it starts to flatten out in this region. You don't really see big changes in B here. But here you see dramatic changes in B, the red balls. If I plot A, the concentration of A versus time, what would that look like? Well, it starts out at a high concentration. It rapidly changes, decreases in concentration, and it flattens out like so at a lower concentration. So the overall rate of this reaction can be written two ways. One is we can say it's the change in the concentration of B over time. And the other way is we could say the change in concentration of A over time. But we have a problem here with A. If you look at A, if I take final minus initial, I'm going to get a negative value here. So if this is 1 down here on this axis and this is 4 up here, I'm going to get 1 minus 3, which gives me a negative, or 1 minus 4, which is a negative 3. So rate's always positive. When you're traveling from Lexington to Louisville, you're going in one direction. The rate's always positive. There is no negative rate. So to make the concentration change of A over change in time a positive value, we have to put a correction factor in here. So that's why we put the negative symbol right here. You see it right there. So that when I put in this 1 minus 4 for my molarity change divided by time, which is always positive, that will give me a negative number, and then multiplying it by this negative will give me a positive number. So keep that in mind. Overall rate is going to always be positive. So this is a great slide. It's a great start. And what we're doing here, we're calculating average reaction rate. We don't know what the rate is at this particular point, and we don't know what it is at this particular point, or we haven't measured it. And we've looked at the rate between these 2 points, and that's an average. All right, so these are both. If we go from here to here, we're not looking at a particular point. That is average rate of reaction. And again, notice what it is. It's a concentration over time. And for us in chemistry, we generally like our concentration in molarity units. So that's why we revisited molarity in chapter 13 before we start talking about kinetics in chapter 14. All right, so notice their plot, maybe not as flattened out as much on the ends here as mine. Maybe I've exaggerated that a little bit. But the reason why they're not really interested in this part as much is that when we get to this part where the rates remain constant, that the rate of the forward reaction or reverse reaction become constant, that's called equilibrium. And we're going to spend about almost 3 chapters on equilibrium. So we're going to mainly focus on what you see in this plot. We're definitely looking at concentration, in this case number of molecules instead of concentration, and then we're going to plot that against time. And I believe you will have a lab in Chem 185 where you'll actually plot the concentration versus time to get a feel for this. But again, we start off with A, 100% A, 0% B. A decreases. Notice it decreases at a faster rate here than it does down here. Same thing with B. B increases in concentration from the beginning of the reaction to the end. So A decreases. I guess I said that. A decreases at a faster rate up at the top here than it does towards the end, and B increases at a faster rate at the beginning than at the end. And we're going to talk about why. It probably seems intuitive that they increase quickly at the beginning. If not, we're going to find out why as we progress through this chapter. All right, so now we have a real chemical reaction, not just A and B, but here we have bromine reacting with acetic acid. And so what we have here is the bromine goes from a 0 oxidation state to a -1 oxidation state. And the carbon is going to be changing, let's see. Well, and this hydrogen is a positive. Let's see, it's actually, yeah, here it's actually a 0 oxidation state, and it's going to a +1 oxidation state. That's where our oxidation reduction is. I mean, you don't need to know that per se to do this problem, but it helps. It's going to help you if you think about what type of reaction this is. This is not a precipitation reaction. It's not an acid-base reaction. We would call this an oxidation reduction reaction. So the average rate is equal to, we can write the average rate in relation to any one of these substances. We could say it is the change in the concentration of bromine over time. All right, the change in time. And again, we'd have to put a negative out here because its concentration is decreasing through the course of the reaction. We could change this, we could say in respect with the acetic acid, we could say the change in, yeah, this isn't acetic acid, this is formic acid. I don't know what I was thinking. Yeah, formic acid. So then we have the change in formic acid over change in time. And again, negative symbol here. We could write it in terms of the bromide ion. We could say that it's the change in the bromide ion concentration over time. Now, here's what's going on here. And here's something you got to really think about. So this is decreasing for every 1 mole of this that decreases per time, we're getting 2 moles of this. So this reaction, the rate of this reaction is going to be twice as fast as this. So we have to put a correction factor in here. We have to put in a 1/2. So that when we multiply 1/2 times the change in concentration of the bromide ion over change in time, the overall rate is going to be the same. So the average rate, or the rate of the overall reaction, can be related to the bromine, the formic acid, the bromide ion, and notice we don't have any negative here with the bromide ion because it's increasing as the reaction goes on. We could write it in terms of the hydrogen ion, and again, it would be the change in the hydrogen ion concentration over a change in time. And again, we'd have to put a correction factor of 1/2 because for every one of these that is consumed, we get, in that same time frame, 2 moles of hydrogen ion. And then the last one is we could write it in terms of carbon dioxide. We say the change in carbon dioxide over the change in time. All right, so these are all averages, and the way we determine the average rate, we have on our plot the final concentration of any one of these substances minus the initial, and then T final minus T initial. And again, because bromine is consumed, if the final is 1 and the initial was 4, 1 minus 4 gives me a -3, and that would be over some time, let's say, I don't know, 10 seconds. 10 minutes. It doesn't matter. It can be any time but this negative, we can't have a negative for our overall rate, our average rate. So that's why we have the correction factor of a negative here. You see it there, you see it there, you see it here. So just keep that in mind. Reactants are going to decrease over time. You would get a negative rate, but the overall rate must always be positive, so we have to put a correction factor in for this. And then again, for every bromine that's consumed, 2 bromides are formed, 2 hydrogen ions are formed. So these rates are twice as fast with respect to each other, with respect to the bromine, let's say that, with respect to this. So we have to put a correction factor of 1/2 in here so that the overall rate, these will all be equal. So rate equals, with respect to the bromine this, with respect to the formic acid this, with respect to the bromide that, with respect to the hydrogen ion that, and with respect to the carbon dioxide that. So this is the important part. Spend time with this, and we're going to see more on other slides, but I just want to point that out, that intuitively you should know that for every one of these that decrease, 2 of these are formed. So yes, the rate of the bromide formation is going to be twice the rate of the bromine consumption. And we're going to see this on other slides. This is your first time. All right, so this is what you're going to be doing in lab. You're going to start out at time 0, and you have the initial concentration of the bromine. And so if I take the concentration versus the time, and it is formic acid, there we go, and we get a rate of 4.20 times 10 to the negative 5th. So that's the initial rate. And so then after 50 seconds, we see a decrease in the bromine concentration. That makes sense because the bromine was a reactant. And so notice the rate has decreased a little bit. Well, we saw that. We saw that when these reactions happen, it starts off fast and then it starts to slow down. So as we progress, you see that the rate is getting less and less and less. And we can also see the concentration of the bromine is decreasing. Although once we get into this region, it's not decreasing by as much. So you're going to collect data like this in lab, and then you're going to plot it like so. And then you can find out additional information from the plot. So again, if I subtract 100 from 50, and I subtract this concentration from that concentration, I'm going to get that's an average. That's an average rate, right? I'm not looking at a particular point, like that particular point. I'm looking at an average rate, so keep that in mind. So the average rate, they said, looking at the data, you look at the first 50 seconds. So the average rate, so read the question carefully. This is the average rate over the first 50-second time interval. You took the final concentration minus the initial, final time, which is 50, minus the initial, which is 0, and that's how we get the average rate of the reaction. The average rate of the reaction. If we choose 100 seconds, you would look at the concentration at 100 seconds minus the time 0, and then 100 minus 0, and we get, this is our average rate. Again, notice this is less than this because we're starting to go down the plot and it's not changing. The rate of change is not as great. Those of you who had calculus, this is easy. I mean, that's the whole thing. If you've had calculus, you're going, oh, this is boring me. If you haven't had calculus, that's what calculus focuses on, especially Calc 1, is rates of change. All right, so a lot of times we're interested in instantaneous rate. We want to know what is the concentration at a specific time. And they say instant in time, but specific time. So I want the average, instead of the average rate, I want the instantaneous rate. And most of the things we're going to do after chapter 1, or I mean after section 1, is going to be instantaneous rate. So how do we find out instantaneous rate? So again, if you've had calculus or to figure out instantaneous, it's the rate, it's the slope of the tangent of the curve at a particular time. So what that means is, if I'm looking at this bromine, concentration of bromine, let's just write bromine, over time, and we know it looks like this. if I want to know what it is right here, I draw a line that only touches the curve at that point, and I get the rise over the run. And they're going to do a much better job than that. So if I want to know what is the point, it's the slope of the tangent. That's what this is, where this line only touches the curve at that point. And then at that point, at that point, I can, I can tell you what it is, what the particular time is, and then I can determine what the concentration is going to be. So how do we do that? Rise over run. And that's what it looks like. So they do a much better job. You see the red triangles. So if I do the rise over the run, the rise, which is the change in y values, divided by the change in x values, that equals the slope at that particular point, and that is the instantaneous rate of reaction. So at 100 seconds, it's 2.96 times 10 to the negative fifth. As the curve flattens out, you notice this number decreases. The instantaneous rate does decrease. So you're going to be doing that in lab as well. So again, we're plotting concentration on the y-axis, time in seconds, and that can be in minutes, hours. The concentration can be actually molecules. If you're taking physics, you're going to be looking at it in terms of nuclei or particles. So it can be very, different types of amounts or concentrations. For us, we're going to use concentration. We're going to use molarity. And for time, it's generally in seconds for us, but it can be minutes or hours. It just depends on how fast the reaction is. So instantaneous rate, remember it's rise over run. It's the slope of the line that touches at one point on the curve. Make sure you know the difference between average rate and instantaneous rate. All right, so what we get here, if we look at average, we look at instantaneous, or we look at two different times, and we get our instantaneous rate, we see that rate is proportional to the concentration of the bromine. All right, so the higher the concentration of the bromine, the higher the rate. So let's go back to that just to show you what we're talking about. If you go back to that plot, you can see that the change is much steeper in this region than down here. It's flattening out. So this is a steeper curve at the top. So when the concentration is high in this region, then the rate of the reaction is also higher. And when the concentration is low of one of the reactants, then the slope is not as steep and the rate is lower here. And that's what they want you to see. They want you to see that. That's the advantage of plotting it out. You can visually recognize what is going on. So if I want to know how the rate is equal to the concentration, we have this K here, which is called the rate constant. All right. So K represents the rate constant, it's a proportionality constant. So we're going to use this the most. Yes, it's great to introduce that rate is proportional to concentration. Higher concentration, the higher the rate. But I want to know what rate's actually equal to. The overall rate of the reaction is equal to a proportionality constant that we call the rate constant times the concentration of the bromine. So we want to solve for that constant. What is the constant? Let's go back to the constant. So let's explain what the constant is. The constant is whatever the slope is going to be through the course of the reaction. Like the slope doesn't, when we divide the concentration at one time versus another, the slope remains constant. The only thing that's going to change the rate constant is temperature. So keep that in mind, that the rate constant that's what it is. It's a constant, and it doesn't change unless the temperature changes. So what we have here is, we solve for K. We're going to take the rate and we're going to divide it by the concentration at one time. And we can take the rate and we can divide it by the concentration at a different time. And notice, when the concentration is higher, the rate is faster. When the concentration is lower, the rate is lower. But when I take the rate versus the concentration, I get approximately the same number. There's a little bit of difference, but not much. And so that's the rate constant. Now, here's what I want you to really get out of this rate constant too, is notice the units. The units tell you what type of rate this is, what's the order of the reaction. And we're going to talk about that, but here's what you got to know. You know that rate is generally in molarity units per time unit, in this case seconds. You know that concentration is in molarity units, so the rate constant has to be 1 over seconds, so that when you multiply these two things together, you get the rate units, molarity per second. So this 1 over seconds, the publisher writes it mostly as seconds to the -1 power. Those mean the same thing, and so that throws some students off. But here's what I want you to get out of it. If you know that the rate constant has units of 1 over seconds, then you know the order of the reaction, or the order with respect to the bromine. So just keep that in mind, and I'll talk about what this order is and what it means. But the rate constant units are going to be really important. They're going to help you determine what's going on with the kinetics of the reaction. All right, so here they're stressing K does not depend on the concentration. It only depends on the temperature. The rate constant is constant at constant temperature. You change the temperature, you can change K, but K does not depend upon the concentration of the bromine in this case. What's going on? All right. So let's look at another reaction. So in this reaction, hopefully you've seen this reaction before. This is hydrogen peroxide, and hydrogen peroxide decomposes into water and oxygen gas. If you've ever had a cut on your finger, here's your real-world application. You've got a cut on your finger. You put some hydrogen peroxide on it. You notice it starts fizzing, and so the hemoglobin acts as a catalyst to rapidly increase the rate of this reaction due to being a catalyst, lowers the activation energy, which we'll talk about, and that's what generates the oxygen gas that you see fizzing on your finger there. So let's talk about this in terms, instead of concentration, let's talk about it in terms of gas. So gas is equal, we've talked about this in Chem 170, PV equals nRT, the ideal gas equation. So the pressure of the oxygen gas that's generated is equal to N over V. So we divide both sides by V here. We get N over V RT. N over V is moles per liter, so that's a concentration. So there's the relationship between pressure and concentration times RT. So if I want to solve for the concentration, it's 1 over RT times the pressure of the oxygen. Why do I need to know this? Because when we're working with gases, we generally don't measure those in molarity units. We generally have a container, and it's sealed, and then we have a pressure gauge over here, And that's knowing what the pressure inside the container is. We know the concentration of the gas. And so that's what we're seeing here, is that rate can not only be written as change in concentration over change in time, it can be written as change in pressure over change in time with this correction factor. So again, we're assuming R is not changing, T is not changing. R, we know, is 0.08206 liter atmospheres mole Kelvin. And again, if you don't remember that, you want to memorize that, go back in chapter 10 and look at gases and look at the units for that, because we're going to be using that as well. So rate, main thing here is rate can be determined by pressure as well as molarity. And so here's an example. We're using a manometer, and so we mix solution together. Well, here's our hydrogen peroxide, and they mix it probably with a little bit of catalyst. That's why it's yellow looking. That causes this to happen fairly quickly, and the hydrogen peroxide generates oxygen gas, and the oxygen gas goes through the tube, pushes the mercury down in the manometer, and we can measure the distance between the mercury, and that will give us what the pressure is. So if we plot this over time, the pressure of oxygen versus time, we can see this chemical reaction happening, and we can see that the instantaneous rate is much faster at the beginning, and again, as the reactant is consumed, then we start seeing it the rate to slow down. So, stoichiometry and the reaction rate. Actually, I've already brought this up, and so hopefully that'll help you remember this a little better. So, what we said was when we look at our balanced chemical reaction, we can see the bromide is going to form at a rate twice as fast. Appears, because it's a product, the rate's going to be twice as fast as the bromine disappears. Same thing for the hydrogen ion. It's a 1-to-1 relationship, though, between bromine and carbon dioxide formed. So it says to avoid the potential ambiguity of reporting the rate of disappearance or appearance of specific chemical species, we report the rate of the reaction. So the rate of the reaction is the overall rate. All right? We determine the rate of reaction such that the result is the same regardless of the species being monitored. Super important right here. We determine the rate of the reaction such that the result is the same regardless of the species monitored. And these are the species. We can measure this rate in terms of the bromine or the formic acid or the bromide ion or the hydrogen ion or the carbon dioxide. So when we have something simple like a reactant going to 2 moles of product B, we know how to write the rate with respect to A. There it is, change in concentration over change in time with our correction factor, because A is decreasing as the reaction progresses. And then B is increasing as the reaction progresses twice as fast as A. So again, the change in concentration of B over time is going to be 2 times that of A. And let me prove it to you. Look at this. If I set these equal to each other, you're going to have the change in concentration over the change in time equals one half the change in concentration of B over time. So, if this is happening twice as fast, then if I multiply 1/2 times 2, that gives me 1, and that's what we have here for that. Now, there's a typo here. This should not have that negative symbol right there. I'll X that out. So there's a typo there. Okay. So can't believe they've made a typo. Well, okay, in general. Okay, so that's what they're making a mistake here. This was related to that. Okay, so then in general, if you have moles of A, moles of B, moles of C formed, and moles of D formed, you can write the overall rate or the rate of reaction as follows. It is 1 over the moles of A of our balanced chemical equation times the concentration change of A over change in time. And again, we have to have a correction factor here of negative because A is a reactant. All right, same thing here. B is a reactant. It would be 1 over the number of moles of B, the coefficient of B in our chemical reaction, times the change in concentration of B over time. And again, a negative here because it's a reactant. Our two products are going to be 1 over the coefficient in C of our balanced chemical equation times the change in concentration of C over time. Same thing for D. So, regardless of what these concentrations are over time, when I plug them into these equations, the overall rate should be the same. So how we say this is, what is the rate with respect to A? What is the rate with respect to B? What is the rate with respect to C? What is the rate with respect to D? But when I plug it into this equation, the overall rate or the rate of the reaction should remain the same. So the correction factors are, we know that the change in concentration over the change in time is a negative value here. So we have to put a correction factor of negative here. And then depending on what this coefficient is, if this was a 2, we would know A is disappearing twice as fast if B is only a 1. So we have to put a correction factor of 1/2 here to fix it. So again, really important that you can write these expressions for the entire chemical reaction. All right, so if you understand what I've talked about here, you should be able to write the rate expression for each of the following reactions. So what they're asking for when they say, so you got to learn the language, rate expression for each of the following reactions. So you're going to write rate of reaction is equal to, and then you're going to write the rate of reaction with respect to each one of the reactants and products. So stop the video, try to do these on your own, and then let's see what you're making a mistake on. All right, welcome back. So right off the bat, for A here, we know, and I'll do one of them, then we'll look at this slide. We know that we have a change in concentration of the iodide ion. And again, if you don't know that's the iodide ion, make sure you are practicing your naming because that's going to be a problem if you can't name these substances. So we have the change in the concentration of the iodide over time. We know we need to put a negative here. We know that iodide is going to decrease over time. And then we have, that's going to be equal to the hypochlorite ion. So we would have the change in concentration of the hypochlorite ion over change in time. And again, we need a negative here because it's a reactant. And then we would have the change in concentration of the chloride ion over change in time. And that's positive because this is going, chloride ion is going to be increasing through the course of the reaction. And then that's going to be equal to the change in the iodide ion over change in time. Again, no negative here for these because these are the products. Easy if you understand it, and that's why you want practice in doing it. So let's look at our answers here. And they look correct. Let's look at the second one. So here you see a coefficient of 2 and a coefficient of 3. Here's where you see the correction factor. So ozone, again, if you don't know that's ozone, make sure you know that one. It's going to come up more than once in this class. So ozone, the change in concentration with respect to ozone, this is, we're losing 2 of these for every 3 of these forming. So the overall rate has to be the same for both ozone and oxygen. So that's why we have a correction factor of negative 1/2. So the 1/2 takes care of the twice as fast here, and then the negative because it's a reactant. And then the oxygen is, for every 2 of these ozones consumed, 3 oxygen are formed. So we need a correction factor of 1/3. So that when I multiply it by this 3 times as fast thing, it cancels out. And again, notice there's no negative because it's a product, and we know that, again, products are increasing in concentration over time. It's not bad. It's not just, you got to know where these numbers come from. This comes from here, and it's, and not just like that. You need to know that for every 2 ozones consumed, 3 oxygens are consumed. But the rate of reaction has to be the same, regardless of whether we're determining it based on ozone or determining the rate of reaction based on oxygen. It has to be the same value here. If it's not, that means you've made a mistake in these correction factors or the signs. So just keep that in mind. And then you can do the last one, see if you understand that one. All right, so that was that's more of a theoretical problem. Here's an application. So it says, consider the reaction of 4 moles of nitrogen dioxide reacts with 1 mole of oxygen to form 2 moles of dinitrogen pentoxide. These are all names we had in Chem 170. All right. So it says, at a particular time during the reaction, nitrogen dioxide is being consumed at a rate of 0.00130 molarity units per second. Now, what does that mean? It means the change in concentration of the nitrogen dioxide in moles per liter over change in time. Notice this isn't the overall rate at this point, or the rate of reaction. This is what I would say is the rate with respect to the nitrogen dioxide. That's how we speak it. The rate with respect to the nitrogen dioxide is 0.00130 molarity units per second. What is the rate with respect to the molecular oxygen? And what is the rate with respect to the dinitrogen pentoxide? So what I would do on this problem, just starting off, I would write rate of reaction is equal to negative 1/4 the change in concentration of the nitrogen dioxide over the change in time. And then I would say that's equal to negative the change in concentration of the oxygen over the change in time. And again, these are both negative because they're both reactants. Then I would write 1/2 the change in concentration of nitrogen dioxide, or dinitrogen pentoxide, over the change in time. All right. So what I've done here is written the rate of reaction, and then how that's related with respect to the nitrogen dioxide, the oxygen, and the dinitrogen pentoxide. So you can see from this, it's real easy once you've written this out. You can see that I want to say 1/4, negative 1/4 of the change in concentration of the nitrogen dioxide over change in time is equal to, and I'm trying to find out what it is for the molecular oxygen, and molecular oxygen is negative delta O2 over change in time. And what they're asking for me to solve for in part A is this part here, the rate with respect to the oxygen. So I'm going to plug this value into here. I'm going to multiply by negative and a 1/4. I'm going to divide by negative right here, and I should get a positive value for the rate with respect to oxygen, although it's going to be a negative value overall, right? Because it is being consumed. So let's look at this on the next slide. They cleaned it up for us. All right, so that's what they did. They set the rate with respect to the nitrogen dioxide. They plug this in, and they get the rate with the overall rate, 3.25. So again, this is the rate of reaction, the overall rate, and this is what it's equal to, each component, like I wrote on the last slide. We know what the rate is with respect to the nitrogen dioxide. We plug it into this equation, and we find the rate with respect to the overall rate. That's what this is. Let's say that. This is the overall rate, or the rate of reaction. This is called the rate with respect to the nitrogen dioxide. All right, so then we set this overall rate, and this is how it comes out to be nice and negative, to what the rate is with respect to the oxygen. So the overall rate with respect to oxygen is negative delta O2 over delta T. So this negative, when we divide over that both sides by -1, we find that the rate with respect to the oxygen is negative 3.25 times 10 to the -4th. So there's two ways to show this. You can write it this way, and you're saying to a person, this is being consumed because it's a negative value at a rate of 3.25 times 10 to the -4 molarity units per second. Or if you say it's being consumed, then don't put the negative sign and just say it's being consumed at 3.25 times 10 to the -4th. Now that's really important because I see this on homework and students get all upset about it. If all they ask you for is the rate with respect to oxygen, what is that value? You would say negative 3.25 times 10 to the -4th. If they say to you, what is the rate the oxygen is being consumed, then we don't put the negative symbol because that is the rate at which the oxygen is being consumed. And then if they ask you for the rate of the reaction, that's the overall rate. The rate of reaction, is always a positive value. So then you would write 3.25 times 10 to the -4th molarity units per second. So what you're going to find out is if you take the value of if you have the overall rate, you can determine the rate with respect to each reactant product. So that's what we're doing. The next slide asks a different question. It says, what is the rate with respect to the dinitrogen pentoxide? So here we have the overall rate, or the rate of reaction, is equal to 1/2, and it's a positive because this is a product, of the change in concentration of the dinitrogen pentoxide divided by time. So if we want to solve for the rate with respect to the dinitrogen pentoxide, we multiply both sides of this equation by 2. And that's what they have here. And so 2 times that value gives me that number. And so the rate with respect to the dinitrogen pentoxide is 6.50 times 10 to the -4th. So the rate of reaction is 3.25 times 10 to the -4th. If I plug this into that equation and I say 1/2 of 6.50 times 10 to the -4th, I want to get that number there. That's the rate of reaction. So here's the rate with respect to the dinitrogen pentoxide. Here's the rate of reaction. Here's the, let's see, if because this says consumed, that's why we don't have a negative symbol here. But if somebody just said, give me the value of the change in concentration of oxygen over change in time, you would write negative 3.25 times 10 to the negative fourth molarity units per second. All right. The reason why we don't see the negative here is because they tell you it was consumed. So they're just looking for the rate. The consumption tells you that it would be a negative value if you wrote it down as a numerical value. All right. I hope that helped. That is the first lecture for chapter 14 on kinetics. And we'll pick up on this on the next video. Thanks.